Okay, I want to do this case study with you. It's a case study review. This is on a Lincoln Navigator I did not too long ago, maybe a couple of months ago. And I don't know the title on YouTube. I guess that's it right there. Lincoln Navigator, low power, P0171, 174, fuel delivery testing. So that is the title of this video. If you guys want to watch it yourselves, I just want to do a rundown as far as the steps we took in here and kind of plug it into where we are with fuel systems. This will give you a good idea of where I want you to be as far as fuel delivery designs. Okay. So going into this vehicle, we have 171 and 174 fault codes, right? Those are my codes in memory. Customer's complaint is the check engine light is on. As far as I know, they weren't really complaining about a low power condition up front going into this, so this is what I see. Next step, what do you guys think you'd want to do? Where are we going? We have lean condition faults. Where would you go next from what I've taught you so far in this class? What's that? I thought you said field trip. I'm like, what? Let's take a field trip. We can do one of those. Yeah, I want to know what my fuel trims are. And before I look at my fuel trim, I want to look at my freeze frame data. Freeze frame data is going to give me a guide as to when this lean condition set. So let's look at our fuel trim data. Sorry, our freeze frame data. This is my capture of my freeze frame. What my main focus is right now, I'm focused on my engine speed, which is not at idle. Okay? And then I'm looking at my short-term trims are 10 and 9. So this is affecting both banks. Long-term trims are 29.7. What can you guys tell me about the long-term in this capture? There is something that you should be able to tell me as far as this 29.7 number goes. I mean, granted, we're running really lean. I get that. That's not what I'm asking you. There's something else in here, and it really has to do with why the short-term is also elevated. And I'm asking you, what about this long-term number? It's maxed out, guys. The long-term trim maximum on this vehicle is 29.7. How do I know that? Because what's the number one job of the long-term? Bringing the short-term back to zero. Why is the short-term not at zero? Because we have maxed the long-term out and the short-term is now adding fuel to, because it's still running lean. This is a pretty bad lean condition. Okay? Just an observation. Not really important for troubleshooting this vehicle, but that's a maxed out long-term. And look at the short-term. It's adding on top of the long-term. So total trim on this vehicle is around 40% additional fuel on both banks.
So that's only because of detonation.
Yeah, detonation, pre-ignition from running lean, correct, low power conditions. You'd think all of that should be here as far as this freeze frame data goes. Here's my suspicion. This is not a vacuum leak. Based on the engine RPM, and then there's another one here. There was an engine load number that I had mentioned in the video. Maybe I didn't catch it here. I had mentioned in the video an engine load of about 80% when we were driving. The vehicle was being driven. So point here, initial view, this is not a vacuum leak. Does everyone understand why I'm not thinking vacuum leak? If this is a vacuum leak, I'm going to see this number more pronounced at idle speeds, and this is a higher RPM, and we're into the throttle a little bit. So I'm looking at my fuel trims live now. After my freeze frame, let's see what's going on. I have a short term that's pretty balanced out there. They're hovering around. Can't really see that here because this is a still picture, but I'm at 25 on my long term, 24. 25%, and my fuel trims, the short terms, are hovering around zero. The next thing I did is I raised my RPM a little bit. And what I'm going after here, let's look at both. Higher RPM. Did it get worse or did it get better?
Worse.
It got worse. So we're on the right track. This matches our freeze frame data. You guys follow my process so far through this. Lean condition. What type of lean condition? Check our freeze frame data, look at our fuel trims, compare what freeze frame data showed me. This matches what my freeze frame data showed me, which is a higher RPM lean condition. I'm thinking, what two main components am I thinking about right now? I've mentioned it countless times. I'm worried about my fuel pressure, for sure, and I'm worried about my mass airflow sensor. Those are my two biggest concerns with lean conditions that get worse at a higher RPM. Okay? So take the vehicle for a test drive is my next thing. And tough to see it in these still captures, but I'm test driving the car right here, and I did 2 wide open throttle runs. I took some notes when I took these pictures so I can point them out to you. That at frame 270, so let's see where that's at here. This is frame 270 right here. There's frame 270 right here, is where I stepped on the throttle to go wide open. Okay? Not a great capture. I was driving the car and talking. My son was with me. He was filming. And I was focused, I knew I was at wide open throttle, and I was really focused in this area. I was looking at the top one, and I was like, oh, that's rich at wide open. What I didn't realize is I had stepped on the throttle here, and I stepped on, the same thing here. This dip right here was the 1-2 shift, so I wasn't too concerned about that. I think that's what misled me here, but here's the point. I'm at wide open. My O2s are not staying rich the whole time like I expected to see. I think in the next page I show this a little bit better. Yeah, I have both runs here. At frame 270, let's get back there again. This is my initial wide open throttle run occurred at 270, and then my second wide open throttle run occurred at 370. So in this area is where I stepped on it. In this area is where I stepped on it. And again, when I was driving it, because I'm driving the vehicle, I was looking at this area here. And what did I say to myself about fuel delivery? I was thinking it was fine. Exactly. I'm rich at wide open throttle, very similar to Brian Strelick's Firebird when we were on the dyno, how we kind of missed that lean condition because the dyno was bogging it down and it was keeping the RPM below 3,500, you guys remember, and my O2s were rich, and the O2s didn't go lean until we went above 35 or above 4,000 RPM. So let's analyze this a little bit. At wide open, it's initially lean. It does go rich, but there's another lean pocket in here. It's not quite all the way rich. This was the 1-2 shift. It only really saw that on the 102, not the other, but I was focused on the wrong areas really when I was driving the car. I really felt like it was okay. I felt like my fuel delivery was fine. You can see it in the test drive. It runs good. I had mentioned, look, it's rich the whole time, but you guys understand it's kind of tough to do this live, right? The data comes by fast, and my eyes got to look real quick at the scan, so I got to make sure I don't wreck into a telephone pole. Okay? So in the video, I missed this, but this is suggesting what? A low fuel delivery problem at wide open throttle. I had a comment from a guy in this video who asked me, he said, he was questioning my wide open throttle test that I've been teaching for years and years, which is at wide open throttle, every car should be rich. And if it's not, fuel delivery. If it is, then fuel delivery is fine. And his question, it was a valid question, because he said to me, that wide open throttle test seemed to be invalid because you said that it was rich at wide open throttle and you have a fuel delivery problem. And I did say that in the video, but I'm telling you guys this now. Was it rich like it should have been at wide open throttle? And the answer is no. This initial lean pocket was there on both sides. See it here too when I first stepped into it. All of this crap shouldn't be there, and all of this crap shouldn't be there. Same way here. We don't want any of this. We don't want any of this. It should have went full rich the whole time, wide open. This test proved to be valid again. Make sense? But I can see why the guy asked me that question. Next page.
Did you explain to him that you fucked up?
No, I didn't. I didn't screw up in a sense that I still went down the right path.
I mean, like how you said in the video.
I did not. There was no way that I could explain to him in this way through a text on the screen. I did explain it to him as best I could. That if you look close at the data, you can see that I misspoke. I believe I did say that. And so, that was up to him to go back and look at it. But I definitely misspoke in the video, saying fuel delivery was good. It was not. The next thing I did after seeing that, I wanted to make sure that my mass airflow looked okay. Still didn't know fuel was the issue. And I was looking at my mass airflow gram voltage, which is going over 4 volts. That's a standard number I use on Fords and all of our analog MAFs. Make sure we're seeing over 4 volts on these. And then I'm looking at a calculated load number of 100%, 101.7. So basically with these numbers, I'm saying this engine is breathing like it should be. So I do not have a mass airflow problem. Okay? You see a load PID that's very, very high, a MAF voltage that's over 4. Nothing wrong with my mass airflow. Nothing wrong with the engine calculation system as far as our volumetric efficiency, how well the engine's breathing. Those numbers are correct. Moving forward. Starting to, I don't remember, I wanted to do fuel pressure. I think that was why. The mass airflow looked good. My O2s showed a fuel delivery problem, so I am based on fuel trim and freeze frame data, not so much on the test drive, but I'm checking my fuel pressure anyway. Okay? So now it comes to where we are here, which is getting into fuel systems and identifying our system design. I'm just pointing out the fuel rail, and what I'm looking for is I'm looking for a fuel pressure sensor, because that's going to tell me what type of system I have. This is a return-less system, meaning what? One fuel line. Let me exit out of here for a second. Okay, I want to talk about this. Here's what I'm thinking about, guys. Is it this design on this truck? This is important for troubleshooting this. Or is it this design? What's different between the two? On the electronic returnless systems, what is missing here that you will see here on this one? Look in here. I have a pressure regulator. See it? And on this one, what's missing? There is no fuel pressure regulator. How is the fuel pressure controlled on this system? If we're not putting a pressure regulator in this car, how is pressure controlled? Yes, we have a variable speed fuel pump. Fuel pressure is controlled by varying the speed of the fuel pump motor. Is that something you need to know if you have a fuel pressure problem? Yeah. Better know what you're dealing with. So how do you know the difference between the two systems? Here's the key. If it is a system that the computer controls the fuel pump speed, there will be a pressure sensor on the rail. What's a pressure sensor look like? 3 wires, 5-volt ref, signal and a ground. No different than the oil pressure sensor you guys checked on that Toyota or whatever it was, Nissan last week. Same exact type of sensor mounted on the rail, 3-wire pressure sensor. So what am I looking for? When I'm doing my visual inspections, I'm looking for a 3-wire sensor that's on the rail. Nothing on this side. Okay? Kind of tough to see the rail in this, but the fuel rail is here. Here's the tube. The rail runs this way. It's underneath that hose. Kind of tough to see here in this still capture. Next slide shows me the other side of this. Really tough to see here. It's dim. This is my Schrader valve right here. I'm sorry for the contrast on the board here, but my rail sits here, comes up this way. There's your main fuel line where it comes in. It's like a spring lock fitting. Rail sits here. Here's one injector connector. Here's the point. There is no fuel pressure sensor on this Ford. Here's the point, because I'm concerned with fuel pressure. I need to know what system I'm dealing with, and this is not a electronic system. Here's the other clue for you guys with electronic systems is there'll be a data PID on the scan tool that says fuel pressure. Not fuel tank pressure. That's for our evap system. It will say fuel pressure or fuel rail pressure. You guys understand the difference? Fuel tank pressure is evap system. Fuel rail pressure would be our injection system. All right. So no fuel pressure sensor, that means it has a regulator. Regulator's in the tank on this one. That unusual one I described to you guys in chapter 14 with the regulator in the fuel filter, Ford doesn't use that. All stuff we want to know. Research experience will teach you. That'll be your guide. Next page. I do a fuel pressure measurement. Schrader valve, nice and easy to connect the gauge. And I have a roughly 42 PSI reading. My camera angle's off there, but about 42 PSI at idle. I don't know my spec yet, but that's what I got. Next thing I do, standard procedure, fuel systems. Snap the throttle to wide open. Sound familiar, Matt, with your Sonoma? What do we see here? I'm at 40 at idle. I snap the throttle to wide open, and it drops to at least 6 PSI lower at wide open throttle. To be clear, this is a dead rev. There's no load on this engine. This is also a drive-by-wire system, which limits how much I can rev it in park. In the video, I sat there and held it at wide open throttle when I was describing to my son. This is a drive-by-wire electronic throttle body system. It's not letting me open the throttle up all the way. So you have to be careful doing these wide open throttle simulated loaded tests based on that variable that the computer may limit throttle opening. But I can still see a pressure drop. So then I look up a spec, and fortunately, with the Snap-on stuff, I can go into the component test meter, which is the Vantage program within the Verus. Some of you guys have been playing around with it here. The component test meter is where I got this info, and it tells me a normal range is 48 to 70 PSI. And in this video, I'm describing why such a wide range spec is being used here. Is there are two different types of systems that Ford runs on this truck. Some of them are electronic returnless, meaning they have variable speed pumps and a wide range of fuel pressures. And the other one is a return type system, which we've described as roughly a 6 to 10 PSI. No, that's the return type. Sorry, let me back up. The two systems would be electronic returnless, variable speed pump, a wide range of pressures, and a mechanical returnless, which would have one set pressure at idle, wide open throttle, the same across the board. You guys understand what I'm saying? So why do we have this wide range? It describes it that I think the Ford uses MRFS as mechanical returnless fuel system. And it actually gives us the description. Fuel pressure is controlled by a mechanical pressure regulator located on the fuel pump module in the tank, so part of the pump. Some vehicles use a fuel pump control module to control the fuel pump module at low and high speeds. Some GTDI vehicles are equipped with a fuel pressure sensor that monitors low pressure. So that would, I don't know why they're calling it a GTDI. What would be the abbreviation for that? It is a electronic returnless system. Okay, that's what that is describing. Here's the point. The big pressure range, I'm on the low end of it regardless, aren't I? I'm at 42 at idle and 34 at wide open throttle. Do I have a pressure problem? Absolutely. I absolutely do. So we need to check the pump. That's where we're going now. I'm back in the back of the vehicle where there is a device called an inertia switch. I know the contrast isn't there for you guys. Let me turn this light off for a second. See the little red tab on top in here? This little red tab? That is your inertia switch. Ford uses that as an impact switch. If the vehicle gets into an accident, it hits this weighted ball. Here, let me show you a picture of it. This is in chapter 15. Just the inside of an inertia switch. What is it? It's just a magnet that holds a metal ball, and it has a plate like a striker plate that in an impact, this ball will leave the magnet, hits the plate, and opens the set of fuel pump contacts, and it pushes the lever. This switch will remain in the upward position. They don't reset themselves. Okay, Ford and Hyundai are the two manufacturers I've seen these on. I've actually gotten paid to go to a body shop to hit a button and say, thank you very much, have a nice day, pay me. Right? It was on a Hyundai that had a subframe put in it. Inertia switch was tripped. Car wouldn't start, wouldn't run. Things you want to remember. But for me, I want to check the pump. I'm not worried about the inertia switch. The fuel systems, this goes right to my fuel pump motor, the inertia switch, and I want to do my pump power and ground testing. So the reason I use this location is I know that inertia switch feeds my pump power and ground. I'm just showing my son with a hammer. I just smacked on the inertia switch, made the vehicle shut off. Just kind of showing him that. This is in the video. Next page, you can see where my amp clamp is. What am I going after here? I'm going after pump current. Why? Because pump power and ground is a little bit more difficult to do. This is my power feed. Can't really get to the ground. I'm in a gravel parking lot. I don't want to lay underneath the car. Similar, Matt, to what we did on Friday on the, what was wrong with that truck? It was a fuel tank level problem, but we had to lay underneath and look at the harness, and I'm trying to avoid that. This is what I do. Standard fuel pump troubleshooting involves using an amp clamp and checking my current flow, and I'll show you why as we continue here. I don't want to lay in the gravel on the ground. I want to know either at the relay or at the fuse, or in this case at the inertia switch, what my pump's doing. So we're taking some measurements. I do ask you guys this stuff on your exam coming up about fuel pump current and fuel pump RPM and speed. So pay attention. You're going to get these answers within this little case study review. Okay? What do we see amperage of my pump? It's right here. 6 amps. This is a 6 amp average. Okay? 6 amps of current. Typical pump current varies depending on the system. 4 to 6 on a low pressure port fuel injection system. Maybe 6 to 10 on a higher pressure port fuel injected system. Matt, your truck would run somewhere 6 to 10 psi, or 8 to 10 psi, sorry, on the higher pressure systems. But I'm at 6 amps of current. Do you see repetition in here, guys? Can you see how the pattern repeats itself? You know, we can put cursors in and say, I can see this low point here, and then I see that same low point there, and then we can measure, calculate one rotation of the pump. That's what you're looking at there. This would be one rotation of this pump. This is 1, 2, 3, 4, 5, 6, 7, 8. This is an 8-bar pump. What do I mean by bar? When I'm talking about the bar of the pump, I'm talking about this guy right here. That's the inside of a fuel pump motor. Those are called commutator bars. And what you'd have is you'd have a positive brush that would ride here. Right? This would go to power, and then you'd have a negative brush that would sit here. Okay, and this would go to a ground. And so we're passing current flow through this motor in a specific direction, and then every 4 it really reverses. If this is positive and this is negative, what happens when that guy moves up here? Vice versa, right? This bar would then become positive, this one, and this bar would become negative. So in any case, we got what? How many bars? 1, 2, 3, 4, 5, 6, 7, 8. Do you guys understand now what's making this pattern? Everyone understand the pattern? The pumps are current flowing through each of those segments. Current rises when it's on a conductor, and current drops when it's on an insulator. So let's go back to that real quick and be clear that this circuit here, or this pump, this is a conductor. This would be the insulator. Conductor, insulator, conductor, insulator. So as those insulators are passing, current's dropping. As the conductor passes, current rises. That's what we're looking at in this pattern. Questions so far? Anything? 8-bar pump. So I want to measure, I'm looking at amperage, I'm looking at pump speed, I'm looking at RPM, but primarily, here's my focus right now. I do not want to check my pump powers and grounds because I don't want to lay on the ground. Is everyone clear on that? I'm going to use current to say I don't have to. And this tells me, this 6 amp average is telling me right off the bat I don't need to check my pump powers and grounds. But we want to make sure that the circuit can pull what it should. I'll come back to the pump RPM measurements because I do that. This is the one I want to see. What are we looking at in this picture without me describing it to you? Can anyone guess?
Starter.
It's not the starter. I'm glad you said that though. Looks, oh, it is startup. It does look like a starter current pattern, which by the way is an electric motor, a DC brush type electric motor. What did I tell you about DC brush type electric motors? How much resistance? How much resistance does one of these motors have when they're stationary and not spinning? Very, very little. So when the motor first turns on, any DC electric motor, when it first turns on, just like that case study we watched last week with the faulty control side of the relay. Remember the video I played on Friday? It was a GM fuel pump relay tester. I forget the title of it. The problem was a bad block ground. It was making the control side of the relay buzz. And what was it doing to the load side? Making the load side switch on and off, on and off, on and off. And it blew the circuit fuse. Why would it do that? Because that initial turn on of that DC electric motor, look how high the amperage is. This is a 22 amp peak. 22 amps of current flow. Okay? Here's the point with this. If I have a power or ground problem to this electric motor, am I going to see that circuit be capable of drawing 22 amps? The answer is no. I have no problem with my pump power and ground. I'm not going to lay on the ground. I'm going to do an amperage measurement. I want to see this spike. Does that make sense? Now, you won't always see 22 amps, and this isn't a test that's going to be like, well, you should see X amperage on this pump. No, I'm just looking for, can this circuit support the current flow that's needed? Because I showed you guys a pump with a bad ground last week too, didn't I? The Ford Ranger, that when you turn the turn signals and headlights on, what happened to fuel pressure? Fuel pressure dropped off the map, didn't it? Can we have a faulty pump, power, or ground cause low pressure problems? Absolutely. So you understand the concern here. This test alone tells me what? Pump, power, and grounds are good. Okay? The rest of this info, the fuel pump RPM, isn't that critical, but once, I don't know if I even need to do it now, but I don't want to leave this open. This is just a more zoomed in view, and I'm placing my cursors here on the unique, what I feel is unique. I can see this low point here, and I see the low point again. This is one rotation of this pump from here to here. Okay, one rotation. What's RPM stand for? Revolutions, rotations per minute. Okay, so if I have one rotation occurring, I need my cursors to see what my time base is. I don't have that here. Didn't capture that quite right. I needed it at the bottom right. Describing it here. Yeah, I didn't show it. I do after, so we'll compare the before and after. But you guys understand what I'm doing? If this is 10 milliseconds, we'll do some easy math. If cursor 1 to cursor 2 is 10 milliseconds long, this pump is operating at 6,000 RPM. Why did I pick 10 milliseconds? Because I can divide that into 60,000 real easy. How many milliseconds are in a second? 1,000. How many milliseconds are in a minute? 60,000. Okay? So that's why I picked 10 milliseconds. You guys understand where I'm getting the 6,000 RPM number with my easy math here? Okay. Typical pump speed I have listed in the book. I don't know that I'm even good with that number anymore, but I have, I think, like 4,000 to 6,000 RPM in that range. But what I'm seeing, it's probably more like 4,000 to 10,000 RPM is a range of normal pump speed. It just depends on the car. My truck, for example, my pump runs at 9,000 RPM. A lot of the other cars you see, they'll run at 5,000 RPM. So it just depends on the manufacturer. We can use that number, though, that will be beneficial. I have a case study where I used that number on a Hyundai to say that the new fuel pump that was put in was wired backwards. The pump was running at 10,000 RPM, and on that particular car it should have been about 5. So the pump was running double the speed because when they put the pump in, they wired it backwards. So the pump was sucking rather than blowing. Can you picture that a pump that's really pulling air, isn't it, from the front? And it's very easy for the pump to spin because there's no fluid there, as opposed to spinning the other way. So anyway, pump RPM can be beneficial. The calculation, this waveform can be beneficial. Not so much here in this case study. I'm just showing the procedure. Do I have enough info to change this fuel pump? Do I have enough info to make the call on the fuel pump? I think so. Powers and grounds are good. Low pressure. You might argue, well, should you put a fuel filter in it and retest it? Sure, you could do that. Is there any test that I can do that's going to tell me my fuel filter is plugged? Let's be clear. Here's my tank. My pump and regulator are inside of here. Comes up to my rail. This is a V8 truck, right? Yes. There's my fuel rail. My filter, inline filter, would be in here. I think it had an inline filter. It might have been part of the tank assembly. My pressure's low. I'm at 42 psi, dropping to 36 psi. Could my filter be an issue? It absolutely could be. Okay. The only way to know that for sure would be I would have to tee a gauge in. Well, I already have one here. I would have to tee a gauge in here. And by teeing a gauge in, I'm saying in parallel to it, not in series, right? Not disconnecting it. You would want to tee that gauge in and then read your pressures here. If my pressures are the same here as here, how's my filter? It's fine. If my filter's plugged, what are we going to see on the left side? Higher pressures. You guys understand how much of a pain in the butt that would be to do that test? Just change the damn fuel filter if you're worried about it. In my opinion, when you have low fuel pressure like this, change the pump, change the filter. Just be done with it. I've had customers come back and MF me, fix the car, plugged filter. 2 months later, customer comes back, bad fuel pump. He's a contractor, needs his truck, it's his job, and he's MFing me that I didn't change the pump 2 months ago, even though I saved him a whole bunch of money. In my opinion, I saved him a whole bunch of money. 2 months later, the pump failed. Ever since then, I don't mess around with plugged fuel filters and fuel pumps when there's decent mileage on the car. If I have low pressure, I'm not even checking it. It's getting a pump, it's getting a filter. That's the call in this vehicle. That's what it's getting. Here's the other thing. Test questions. I ask you, causes of too high of amperage, causes of too low of amperage, fuel pump amperage, fuel pump current. Would a plugged filter cause this pump to build higher than normal pressure in this area? Answer is yes. So what would my amperage of my pump do if my filter was plugged? It would climb. Now, this would be where knowing your system helps. I'll tell you this much. My average amperage before, this is my 6 amp average. Let me show it to you after I change the pump. We'll get to the pressures here in a second. Look at my average amperage after changing the pump. New pump, new filter. Amperage is higher. Was this ever a plugged fuel filter? No. Plugged filter is going to do what to your amperage? It's going to raise it. So you see we can use amperage as a guide too as far as a plugged filter goes. But this is the pump amperage, the new pump. We'll talk about that. Let's look at our pressures first. So I replaced the pump, and the big picture here is my fuel pressure at idle. It's a huge difference, isn't it? It's a huge difference just at idle. You guys remember my fuel trims were positive at idle too when we started this? They were about 25 on the long term and 0 on the short term. Raised the RPM and it went 30 and 10. So it did get worse, but it was bad at idle too. And to the rookie, maybe that looks like a vacuum leak. It's not. It was bad at idle, so it messed up my fuel trim numbers at idle too. This is my number, 64 psi. Here's the before. I was at 42. This is after. This is at idle. What's this one right here? This was idle before. About 42 psi. Snap the throttle, drops down to about 36, 35, somewhere in there. 3-4 psi drop. Okay? Big time difference. I didn't like this though. I snapped the throttle and I noticed this. And in the video you'll hear me talk about it. What am I seeing? I'm seeing a pressure drop. It's very momentary. It does happen. Initial snap. I want to tell you guys about these returnless systems. The regulator is in the tank. So when I snap the throttle and my pressure loss occurs up at the rail, there's a little bit longer response time for the regulator to account for that. It is normal on returnless systems when the regulator's in the tank to get a few psi, initial snap throttle, a few psi drop in pressure on these systems, just because the regulator timing takes time for that regulator to account for a pressure change. Can everybody visualize that without me going to the picture? Picture the regulator in the tank. The pressure loss occurs at the rail first. The injectors fire. Where's my pressure gauge connected? On the rail, right next to the injectors. Pressure drops momentarily, regulator accounts for it, closes, raises pressure back up. This is not a problem. I know we used this as a guide before we started and said this was a problem, but technically speaking, it never really was that part that was the problem. Look, it's my pressure overall is low, isn't it? Overall. If I could have test driven this, we would have seen this gauge dropping, I think, at least a little bit. The pressure was high enough to give me misleading oxygen sensor signals, though. It really never exhibited a low power complaint. Huge difference in pressure, guys. Huge difference. Amperage looks pretty good, doesn't it? It's higher than 6. Again, no plugged filter. I'm putting my cursors where unique humps are. And the thing about brand new fuel pumps, sometimes you can't see unique characteristics because the pump is brand new. And in fact, some pumps will actually give you very, very poor amperage patterns when the pump is new because the brushes haven't seated in yet. Okay? Especially on the side-mounted ones, when you have a side-mounted brush, so the brushes come in this way, and they would sit on the side of that pump. I can't draw this like rounded, but this is actually a round piece, and these are square cuts, so they never really make good contact until they seat in. Just be aware of that. If you're ever doing pump current measurements on a scope, the new pattern can look messy. This one, I'm trying to get a good gauge of where those are. So I'm changing my amperage levels. This is at a 20 amp scale. I changed it to a 10 amp scale, which made it bigger. And then I really was having a difficult time because I counted my numbers. And so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I had an 8-bar pump when I started, and now this is a 10-bar. And I was questioning that as being an accurate measurement because I wanted to give good before and after RPM measurements. They do make 10-bar pumps. This is a 10-bar pump. And the next page, see if you guys understand what I did here. Change this. How did I make it look like that? Look at my scales to the left. See how many of you guys were paying attention with the scope stuff. What did I do? I AC coupled this. What's that mean? If you AC couple the scope, I eliminated all the DC. So you see my 0 amp number? So I eliminated it's taken this 8 amp average, it's taken this, and it's bringing it down to 0. And so what that allows me to do is change my scales now to I believe this is a 1 amp scale. Yeah, look at my peak, it's 1 amp. And so it allowed me to magnify that waveform. It's how you have to do it with the Snap-on stuff. On my Pico, I can just zoom in on it. But on the Snap-on stuff, you pick AC couple, and it eliminates the DC average behind it, puts your line at 0, and now I put my cursors in there, and I'm measuring pump speed. Somebody break out your calculator for me, because I put the number up here. I said the pump was running 8,438 RPM before. I know we didn't have our numbers to calculate that. Here's our new number. One rotation is 9.33 milliseconds long. So go, let me count my bars here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a 10 bar pump. One rotation is occurring every 9.33 milliseconds. So go 60,000 divided by 9.33. Somebody do that for me real quick. 6,400 and what? 30. That's interesting. So if I would have known a little bit more about this system, I said somewhere between 4,000 and 6,000 is what I have listed in my book, though I did say some pumps run at higher speeds. Here's my before number. Here's my after number. The pump actually slowed down. My amperage increased. The pump speed slowed down. What was wrong with the original pump? There was a mechanical problem with it. The original pump, based on these numbers, had a mechanical problem, not an electrical problem. My amperage was low because that impeller was damaged and either slipping or not pumping like it should. Maybe one of the fins were broken. It was allowed to spin a lot faster and not produce as much pressure that we needed. We can see that in these before and after numbers. Here's the point. Is measuring fuel pump current, is that going to benefit you at some point in time? Yes. Is calculating fuel pump RPM going to benefit you at some point in time in troubleshooting? Absolutely. Is knowing how to look at these waveforms, put your cursors in there to calculate this necessary? Yes, it is. And then the final one too is how important is this test? This is the new pump. After I'm done, initial turn on, what do we see about the current flow? Same as the old one. How's my pump power and ground on this vehicle? It's good, right? This is all the procedures that we're going to be talking about in chapter 14, chapter 15, chapter 16, what we're covering now. All this stuff really plugged into one video. Final thing, and then I'll let you guys leave. These are the after. Kind of tough to see these numbers, so I cut it off. These are the after fuel trim numbers. Car's idling. We were at what before? Long terms were at 25 at idle. Short terms were around 0 where they are now. But look where my long terms are now. 9 and 10. It's not perfect. It's not perfect, but did we have a huge improvement? Plus and minus 10% is considered normal. Let's go to the next page. This is a higher RPM. How my numbers look? 8 and 5. They got better, didn't they? Worse at idle, better at a higher RPM. There's a good chance of what on this truck? What do we have? What do we have problem-wise here? Fuel trim numbers that are 9 and 10 at idle and 8 and 5 at a higher RPM. What, Dustin? Vacuum leak. This truck probably has a small vacuum leak. Here's the thing for me. Do I care right now? If it's my car, maybe I'll look a little more. Do I care as far as my fuel pump diagnosis goes? Did I make the right call? Higher RPM last time, it was at what? These numbers were at 30. 30 and like what? 12 and 10, I think? I wrote that under the O2. That'd be my short term. My short term was 12. Short term was 10. Did we have a big improvement here by changing the pump? Is there still a small issue left, possibly? Is plus and minus, these are still within spec though, aren't they? 9 and 10. Is this going to set a check engine light? This is the most important part for us as technicians. It's not. Did we fix this vehicle? Yes, we did. Is there a minor issue here? Maybe it'd be worth doing a smoke test on at the end? Sure, why not? Did I do it for this video? No, I didn't. My main point with this video was fuel pump diagnosis. This is what it's about. Knowing how to do all these procedures, putting them all together, what we're learning now, and doing it on the car.